Okay, so we're now going to be looking at friction. So all this time previously, when we've been dealing with these kind of questions, we've been told that it's like a smooth surface, right? And what the smooth surface represents is that the assumption that there's no friction. But from now on, there might be a certain situation where the question says the surface is rough. If the question says it's rough, it means that there is a friction, and therefore friction is an additional force that we're taking into account of when we're resolving for forces. Right, so the way we work out the frictional force is this equation here. So F max is mu times R. R is just a reaction force which comes from when something is on the top of a surface, right? Acting always perpendicular to the surface. Mu is something called a coefficient of friction, and it's between a value of 0 and 1, so it has a range, okay? So it can't be bigger than 1, it can't be a negative number. If it's 0, it means that it's a smooth surface. If it's 1, it means it's rough. So the closer it is to 1, it's more rough, basically. So if you do mu times R, it gives us something called F max, or friction. And we call it max friction because that's the maximum amount of friction the surface will give out. If it doesn't have to give out the maximum amount of friction, it won't, but it just means that that's the limit of the frictional value it could give. So if you have this situation here, we have the particle weight 10g, we have a tension force pulling it to the right, and therefore the friction is going to be acting opposing the motion. So if it's moving right, then the friction is going to be moving left. And so what we're going to do now is we're going to be resolving vertically and horizontally. So if I was to do vertically, F is ma, then we get R minus 10g is equal to 0 because it's not accelerating up and down, right? If I was to resolve horizontally, then we have F is ma again, we have T minus friction is equal to mass times acceleration. It could be moving, so we'll leave it like this. So therefore we can say that, well, R is going to be equal to 10g like so. Now, if I give it a coefficient value, let's say the mu is a half, okay? So mu is 1 over 2. Therefore, if R is 10g, then the frictional force is going to be 10g times a half, which is going to be 5g, or 49 newtons. So this is the maximum amount of friction that this particular surface will give with this particle on top of it. Now let's take a look at some scenarios. So let's say, first things first, let's say T is equal to, let's go for 20 newtons, okay? So if I plug in 20 into here, right, that's the reaction force, or resolving horizontally, then we get that 20 minus friction, which is 49, is equal to the mass 10 times by A, which means that A is going to be equal to minus 2.9 meters per second squared. Now what this means is that, well, if it was accelerating this direction here, right, then acceleration, if it's negative, means it's going back. And this is the case why we say it's F max. As you can see, if we did a resolving calculation, it means it's negative 2.9. However, it's weird for the friction to pull it right back, right? So the friction only opposes it. It's not going to be pulling it back. So in fact, in this certain situation, the amount of friction that they're going to actually be using is the 20 newtons. So the amount of friction given will be 20 minus 20, which is 10 times A. So acceleration will be 0 in this situation. That's why we call it F max. That's the maximum amount of friction it can give. Let's look at the second scenario. So let's say that tension is equal to 49 newtons. So let's replace it again. So 49 minus 49 is equal to 10A, and as you can see, A is equal to 0. So this is a case where the maximum amount of friction needs to be used to prevent it from moving. And so what we call this a limiting equilibrium, because the particle is still not moving, it's still in equilibrium. However, any more force to tension is going to be applied by will make it start to move. So this is the point of it moving. It's on the point of movement, that's what we call it. And finally, let's go for when tension is equal to 99 newtons. So same situation, we're going to do calculation. We have 99 minus 49 is equal to 10A, which is 50. So A is going to be 5 meters per second squared. So in this case, the particle is going to start accelerating. The tension force is greater than the maximum friction force, so it's going to overcome the friction and then it starts to accelerate. So you can see I have 3 different scenarios depending upon the value of the tension, whether or not the particle will accelerate or not. Right, let's look at this question here. So a train of mass 20 kilograms sits at rest on a rough horizontal plane. So let's go by drawing it first. There's a horizontal plane, like here. Its weight is 20g, and we've got its reaction force going upwards. A force of 20 newtons acts on the trailer at an angle of 30 degrees above the horizontal. So a force of 20 newtons, like here, acts at an angle of 30 degrees above the horizontal. Given that the trailer is in limiting equilibrium, which means that it's not moving, but on the point of moving, which means that acceleration is equal to 0, work out the coefficient of friction. We're trying to find this mu value. If it's pulling to the right, it means that friction must be to the left, right? Because that's going to opposing that motion, which is going to the right. So we're trying to find the friction. So first things first, we need to work out, or we need to resolve vertically and horizontally. So let's start off with vertically. So we have the reaction force acting upwards, so plus R, minus the weight, 20G. But we also have this component of the force which is pulling, right? Because it's at an angle. So it's got some component acting upwards, which would be 20 sine 30. So this we need to include, so that's going to be plus 20 sine 30 degrees. And that's going to be equal to 0 because it's not accelerating in the vertical plane, it's only accelerating horizontally, so it's going to be equal to 0. So therefore R is going to be equal to 20G minus 20 sine 30. Right, now let's now resolve horizontally. So we've got the component of the force 20 acting horizontally with this component here, right? Which would be 20 cos 30 degrees. And then we have the minus friction, and that's equal to mass 20 times acceleration, which is 0 because it's in the point of, it's in limiting equilibrium. Right, in order to find this, then friction will therefore be 20 cos 30 degrees. Right, we're trying to find mu, and we know that equation that friction is equal to mu times R, right? Which I can rearrange to get mu is equal to friction divided by R. And we got friction here and we got R here, so I just have to divide it. So mu would therefore be friction, which is 20 cos 30 divided by 20G minus 20 sine 30, like this, which would give me 0.09. One tip is when you're doing these calculations, I'd recommend you using these exact values, okay? Because you can plug this into the calculator and get a certain value, right? But when you're actually doing the calculation, I would recommend you doing like this, using the exact value to do the division. That way the answer is as accurate as possible. Right, the second example, a particle of mass 0.5 kilograms is sliding down a rough slope angled at 15 degrees to the horizontal. So now this is an inclined slope like here, inclined at 15 degrees. And the particle is mass 0.5 kilograms, 0.5 G, and it's sliding down, which means it's accelerating in this direction here, right? The acceleration of the particle is 0.25, so this is going to be 0.25, like so. We have the reaction force acting like here, and if it's moving down, friction is going to be acting up the slope because it's trying to prevent it from moving downwards, right? And they're asking us to find the coefficient of friction, so they're asking us to find the mu value again. So remember for incline, so rather than resolving horizontally and vertically, we're going to be resolving perpendicular to the plane, and we're going to be resolving parallel to the plane, okay? So resolving perpendicular to the plane, F is MA. We have this R value up there, and we have this minus 0.5G. Remember, we want this component acting perpendicular, so this one here. So it's going to be minus 0.5G cos 15 degrees. And that's going to be equal to 0, because remember, it's not accelerating in that direction. So R is going to be equal to 0.5G cos 15 degrees. We can also resolve going down the plane because it's moving down, so down is positive for us in this situation. F is MA. Well, we have the weight component acting downwards, so this component here. So that's going to be 0.5G sine 15 degrees. And then we have this friction acting upwards, so it's going to be negative friction. It's going to be equal to mass 0.5 times the acceleration, which I've told us is 1 over 4.25, like this. Which means that friction is going to be equal to 1 over 8, also 0.5G sine 15 minus 1 over 8, like so. And remember, we're trying to find mu, right? And mu we know from the equation, F is mu R, is friction over R. So mu we can say is going to be 0.5G sine 15 minus 1 over 8 divided by 0.5G cos 15, and you should get a value of 0.242. The mu value of the coefficient of friction has no unit, so it's just a number, so you just leave it like this. Let's try another example here. So we have a particle of mass 2 kilograms sliding down a rough slope that is angled at 20 degrees to horizontal. So once again, it's a rough slope, like this. The angle is 20 degrees. Particle 2G. If it's going down, then the friction has to be going up, like so. And we have this reaction force like this. A force of magnitude P acts parallel to the slope and is attempted to pull the particle up the slope. Okay, so there's another force P, which is acting up the slope like here, and it's attempting to pull it back up. The acceleration of the particle is 0.2 meters down the slope, so it's going to be acting downwards with 0.2 meters per second squared. And the coefficient of friction between the particle and the slope is 0.3. And they're asking us find the value, so this is P, find the value of P. So first things first, we need to work out FR, all these different things, right? So let's resolve down the slope, down is positive. So we have the 2g component, the sine 20 acting down the slope. We have this friction acting opposite minus friction. We also have this P acting opposite minus P, and that's equal to 2 times 0.2, right? Like this. Right, we have two unknowns with this friction and this P, and we're trying to find this P value, so we need to work out the friction. Like we know friction is mu R, and we know mu is 0.3, so all we need to do is find this R value here, right? And in order to find the R value, I'm going to resolve perpendicular to the slope. And we have that R minus 2g cos 20 is equal to 0. So therefore R is going to be equal to 2g cos 20, like this. Now we find R friction, remember it's mu times R, so friction is going to be equal to mu, which is 2g, so 3/10 times R, which is 2g cos 20 degrees, like so. So this will give you 0.6g cos 20. Now we find R, we can go back to the initial resolving we did here, right, in this initial place, because we have this friction, don't we? So I can replace this frictional value into this frictional position here, and that way I can rearrange to find my P value here, and that'll be the P value that I want you to find. Okay, let's try this one last one. So we have a particle of mass 5 kilograms is being pushed up a rough slope. So we have a slope again, angled at 30 degrees. So the mass of the is 5, so it's 5g like this, and it's being pushed up. So therefore the friction, if it's moving up, the friction has to be opposing it. So friction is going to be moving downwards. It's being pushed up by a horizontal force of P. So P is acting horizontally, meaning it's going to be acting in this direction here, P. Given that the coefficient of friction is 0.2, so mu is 1/5, and the acceleration of the particle is 2 meters per second, it's moving upwards like this at 2 meters per second squared. Calculate the value of P. Remember, we have to include the reaction force like so. So you just need to be very aware of how to draw these force diagrams. So it's the same concept that we're going to be resolving perpendicular and up the slope. So let's resolve perpendicular first, like this. Right, we have this reaction force going upwards, we have the weight component going downwards, so 5g, in this case it's doing cos 30 degrees. And we also have this P component, right? Because this P1 I can separate into going like here and here. So we want this angle here, which is the same angle, 30 degrees. So the component acting in the perpendicular direction will be negative P sine 30 degrees, and that's going to be equal to 0 because it's not moving up or down. So therefore we know that reaction force is going to be equal to 5g cos 30 plus P sine 30. This is needed because we need to work out the friction, right? And friction we know is mu R. So mu is 1/5, so it's going to be 1/5 times 5g cos 30 plus P sine 30. So we found out our frictional force first. Now I'm going to be resolving up the plane. Okay, so we have pushing up, we have the P component, right, which is P cos 30. We have the weight acting downwards, so that's going to be negative 5g sine 30. And we also have the frictional force acting downwards, so minus friction. And that's equal to MA, so 5 times A, which was 2. Okay, and so therefore, that's why we have to find the friction, because I can replace the friction into this section here. So we'll have P cos 30 minus 5g sine 30 minus, now we have g cos 30 minus P/5 sine 30, and that's equal to 10. Now just a matter of rearranging and simplifying to get my P, and P you should get as 56.1 newtons. So you can see that we needed the friction value. You always need to find the frictional value first in order to find certain accelerations or certain forces. So first things first, you should always be resolving perpendicular to the plane or vertically in order to find this reaction force, in order to find the frictional force.